Hello students, we will continue the factors affecting acidic strength. We already studied about dissociation constants of weak acid and weak base. Now apart from Ka value, there is any factor deciding acidic strength if you want to study? There are two major factors. The first one is the strength of the bond and second one is the polarity. Okay, so let me explain these two in detail and then we will take up an example. Suppose the bond between H and A, H for a hydrogen and A for an acid radical in an acid, if the bond becomes weaker, then breaking of bond becomes easy, more number of H plus ions are produced. So as the bond strength decreases, the first thing you have to understand, if the strength of the bond between hydrogen and A, if it is decreasing, then the acidic strength increases. Artha aita? So yavaga bond weak agtade, aga H plus A minus ions easily formation agtade, so it will become a more stronger acid. Now second thing is about the polarity. Whenever there is a larger difference in the electronegativity, you know what is polarity, you already studied, the charges produced on the different groups. When there is a larger difference in electronegativity, there will be more charge separation. If I say this positive and negative, more charge produced on the atoms here, then what happens? The breaking of bond also becomes easier. Bond strength decreasing and breaking of bond becomes easier. So polarity is also deciding the bond strength and in turn it decides the acidic strength. Okay, so now considering these two factors, down the group and along the period, how they have an impact on the acidic strength. Now let me take up example, hydrogen fluoride, hydrogen chloride, hydrogen bromide and hydrogen iodide. These four acids. Among these four, which is having a maximum acidic strength? Now you have to understand, among this strength and polarity, which decides the acidic strength. Okay. Important thing you have to understand, hydrogen is common everywhere and fluorine, chlorine, bromine, iodine, so it is down the group and we can understand that is a negative ion forming species here. We compare the size of that. Okay, so we all studied in the periodic properties, down the group atomic size increases. Okay, so among fluorine, chlorine, bromine and iodine, iodine is largest in size. Okay, you studied in chemical bonding also. Now down the group when atomic size increased for the negative ion, the strength of the bond decreases. Okay, so when the strength of the bond decreased, dissociation becomes easier and acidic strength is increasing. So you can remember, among HF and HI, which is the strongest acid? It is HI. Okay, why HI is a stronger acid? Because larger size of iodine, strength of the bond decreases, dissociation becomes easy. So comparing the acidic strength among hydrogen fluoride, hydrogen chloride, hydrogen bromide and hydrogen iodide is having a maximum acidic strength and we can understand it is down the group we compare. Atomic size from left to right we can consider here from HF, HCl, HBr and HI, the size increases. When the size increased, acidic strength increasing. Okay, in this case acidic strength increasing with respect to the size, that means deciding the strength of the bond. Okay, now consider the elements in the same period. Okay, let me take up example of methane, ammonia, water and HF. So what you can understand here, carbon, nitrogen, oxygen, fluorine in the same period. So along the period, now the atomic size is decreasing. Okay, and one important thing you have to understand, in this case more than the atomic size comparison, we look at the electronegativity. Okay, the polarity, the second factor is significant here. So here what you can understand is, from carbon to nitrogen, nitrogen to oxygen, oxygen to fluorine, electronegativity increasing. So we can understand in this series, electronegativity increases. When the electronegativity increases, then also acidic strength is increasing, because I told you already, electronegativity decides the polarity, polarity decides the strength of the bond, strength of the bond decides the dissociation rate. So here among these you can compare, as the electronegativity is increasing, acidic strength is increasing from methane to ammonia, ammonia to water, and ammonia to water to HF. Okay, so this is simple about the factors deciding or affecting acidic strength. So you have to remember these two factors, strength and polarity. Strength depends on the size of the atom, polarity depends on the electronegativity. Are you clear? So this is simple. Okay students, now we'll understand one more important phenomena here in the equilibrium, that is about the common ion effect. As the name itself indicates, in the presence of common ion in the equilibrium, there is a shift of equilibrium. Okay, so how the common ion effect can be explained? Before I tell you the definition, let me give you simple example. Let me take up a weak acid, acetic acid, CH3COOH. You all know acetic acid is a weak acid. In the aqueous solution it is present, it undergoes a partial dissociation to give acetate ion CH3COO minus and H plus. Okay, acetate ion is also in the aqueous form, H plus is also in the aqueous form. Okay, now there is a partial dissociation because it is a weak electrolyte or a weak acid. Now suppose to this solution I will add again acetate ion. Maybe I am adding sodium acetate salt or some other way, or just I am adding acetate ion. Now whenever I add acetate ion, what happens is the concentration of H plus will be decreased, because you have to understand the shift of equilibrium takes place. Okay, let me give you a very simple example. Maybe you people sitting along with your friends and talking, commenting about one of your friend. Okay, suddenly if that person comes to that place, now what will happen? You will change the topic. Correct, no? You may not be worried, but still you may change the topic. So here, in the presence of the common ion, the dissociation rate is affected, or there is a shift of equilibrium. So that phenomenon is called as a common ion effect. So you have to just understand the definition, but this common ion effect has got a large number of applications in the solubility equilibria. You have to understand in the qualitative analysis and many more. But first try to understand what is common ion effect. Okay, so how you can define the common ion effect? Simple, I told you, when you add the ions which is present in the equilibrium reactions, then it will result in the shift of equilibrium. So how can we start the definition of common ion effect? Common ion effect is a shift of equilibrium. Okay, try to understand. So it is somewhere connected to the Lee-Chatelain's principle, what you studied in the previous part of this chapter. Okay, so common ion effect is a phenomenon in which there is a shift of equilibrium, okay, by the addition of a common ion or by the increase in the concentration of the one of the ionic species, okay, in a equilibrium reaction. Are you clear? The shift of equilibrium by the addition of the common ion or by the increase in the concentration of the ionic species which is already present there. Okay, so what I am telling, common ion means the ion which is already present in the solution. If that ionic species concentration is increased, then the shift in equilibrium, whatever happens, that is called common ion effect. Are you clear? So this is one of the example. You can take up any other example also. If I take HA, a weak acid, it dissociates forming H plus and A minus. Okay, now if I add some other substance which will produce A minus, okay, say for example I'll add a strong salt Ba, it will form B plus and A minus. Now what happens? The common ion is this A minus. Now as soon as the concentration of A minus is increased, the equilibrium is affected. Okay, so there is a shift of equilibrium takes place in the first equation in the equilibrium reaction. Okay, and that is called common ion effect. So we are adding the ions which is already present in the solution. Okay, and that particular ion is called common ion. So you remember only this much here in the common ion effect, that is sufficient. Okay, applications and more details are there that you no need to worry. Clear? So that is easy about common ion effect. Okay students, now we'll study about one more small aspect, that is about a buffer solution. It also works on the principle of common ion effect only. Okay, so we have to understand what is buffer solution and what are the different type of buffers. Okay, so when I use the word buffer solution, You have to remember there are many body fluids like blood, urine, you can understand. In a human body itself, they have got a particular pH. Okay, if there is a slight change in the pH of a blood, will affect in the normal functioning of the body, or it may lead to the malfunctioning of the body. Okay, so how it is possible to retain the constant value of pH? Okay, so now one of the simplest examples for a buffer solution is a blood in human system. Okay, so how it will retain the constant value of pH? Okay, that mechanism is there, but try to understand first what is buffer solution and what are the different types of buffers. Buffer solution is a solution, simple definition, which can resist, which can resist the change in the pH value on dilution or the addition of a small amount of acid or alkali. Andre dilution ಮಾಡಿದಾಗ ಅಥವಾ small amount acid ಅಥವಾ alkali ಅನ್ನು add ಮಾಡಿದಾಗ pH value constant ಆಗಿರಬೇಕು. There is no change in the pH value. Such solutions we call it as buffer solution. I repeat, buffer solution is a solution which can resist the change in pH. Okay, solution which can resist the change in pH on dilution or when small amount of acid or alkali is added to it. Okay, now we have to understand there are the different types of buffers. The first one is called acidic buffer, second one is called basic buffer, and third one is called as a neutral buffer. Now just understand the composition of this. Acidic buffer will have a weak acid and its salt with a strong base. So as I told you earlier, common ion effect plays an important role here in the mechanism of buffer action. So it will have a weak acid and its salt. Say for example, if I write CH3COONA, CH3COOH, sorry, acetic acid, if it is mixed with the CH3COONA, sodium acetate, it will become an example for acidic buffer. Okay, so it is a mixture of a weak acid and its salt with a strong base. Basic buffer will have a weak base like ammonium hydroxide and its salt with a strong acid, so ammonium chloride, if I add, it becomes a basic buffer. Okay, a neutral buffer is a combination of weak acid and weak base. It is a single salt buffer like these two if I mix together, weak acid and weak base, ammonium acetate CH3COONH4, it becomes a neutral buffer. So first of all you have to understand what is buffer solution, then you have to remember the different types of buffers: acidic buffer, basic buffer and neutral buffer. Okay, now one more small aspect here which is excluded from the syllabus for this year, that is Henderson's Hasselbalch equation for the pH calculation in the acidic buffer and pOH calculation in the basic buffer. I'll just mention the expression and the derivation is not there for the syllabus for this year. So Henderson-Hasselbalch equation for acidic buffer is, for the acidic buffer we can write as pH is equal to pKa plus log of concentration of salt divided by concentration of acids. Okay, this is called Henderson-Hasselbalch equation for an acidic buffer. pH is equal to pKa plus log of salt by acid concentration. When all these values are given, you can find out pH there. So you know that pKa is minus log to the base 10 of Ka. Salt concentration will be given. We know that will have a salt which contains a common ion. Acid concentration will be given. So basic buffer, again the very similar expression is there. That is also Henderson-Hasselbalch equation. In terms of pOH is equal to pKb plus log of concentration of salt. See, almost remains same, but instead of acid it remains a base. Instead of Ka we say Kb, instead of pH we say pOH. This is a Henderson-Hasselbalch equation for a basic buffer. Okay, so these are the two expressions in the calculation of pH and pOH you can use Henderson-Hasselbalch equation. So anyhow you have to remember what is buffer solution, what are the different types of buffers, and Henderson-Hasselbalch equation. The derivation of this is excluded from the syllabus for this year. Okay, so that is easy about buffer solution. Okay, are you clear? So simple, remember these two expressions. The problems, numericals may be asked based on this by giving all the values directly. You have to substitute. If not the pKa given, Ka will be given. You have to know the formula to convert the Ka into pKa, that is negative logarithm to the base 10 of Ka gives you pKa. Okay, so the concentration of salt and acid will be given directly, then you can substitute and simplify to get the answer. Okay, so that is easy about the buffer solution. Okay students, after understanding about the concept of common ion effect and buffer solution, now let me move on to solubility equilibria of a sparingly soluble salt. Okay, you all know what is a salt, you know what is a solubility, but try to understand what is the difference between a simple salt which is soluble salt or a sparingly soluble salt. Okay, so basically when you have to understand, like when sodium chloride added to water, it dissolves. When calcium carbonate added to water, it will not dissolve. And same sodium chloride salt may not dissolve in some other solvent. How it dissolves in water, it may not dissolve in some other solvents. Okay, yella salt to yella solvent alli dissolve agbeku anta enilla. So now you will ask a question with a curiosity. Now what is that factor deciding which substance will be soluble in which solvent? Okay, you all heard about the basic things, you all know, polar solvent, non-polar solvent. Water is an example for a polar solvent. Benzene is an example for a non-polar solvent. Okay, most of the salts are easily soluble in polar solvents. Okay, now the question you will arise in your mind, what is that factor deciding the solubility? Okay, so you have to understand, students, here a very simple thing. The two important energy values decides is it the substance is soluble in a given solvent or not. Okay, that two are, one is lattice enthalpy or lattice energy, and other one is solvation enthalpy. Automatically you'll ask a question now, what is this lattice enthalpy, what is the solvation enthalpy? Okay, now when you say in case of a salt, the ions are closely packed. If they are closely held, between them there is a force of attraction, that is usually we call it as a lattice enthalpy. Okay, and depending on the nature of the solvent, how the ions will be surrounded by the molecules of the solvent. Okay, and that is solvation enthalpy. So you have to understand, lattice enthalpy depends on the nature of force between the ions in a solid. Solvation enthalpy depends on the nature of the solvent. Okay, now some of the solutes are completely soluble, some of the salts are partially soluble, some are completely insoluble. So how can we predict the given substance is soluble or insoluble? It is very easy, you have to understand. Remember, among these two enthalpy values, whenever solvation enthalpy is more than lattice enthalpy, then the salt is soluble. ಅರ್ಥ ಆಯ್ತಾ? ಈ ಎರಡು ಎನರ್ಜಿಯಲ್ಲಿ ಎರಡು ಎಂಥಾಲ್ಪಿ ಕ್ಯಾಲ್ಕುಲೇಷನ್ಸ್ ಅಲ್ಲಿ ಕಂಪೇರ್ ಮಾಡಿದರೆ ಯಾವಾಗ ಸಾಲ್ವೇಷನ್ ಎಂಥಾಲ್ಪಿ ಹೆಚ್ಚಾಗ್ತದೆ ಲ್ಯಾಟಿಸ್ ಎಂಥಾಲ್ಪಿಗಿಂತ, ಆಗ ಆ ಸಾಲಿಡ್ ಡಿಸಾಲ್ವ್ ಆಗ್ತದೆ. ಓಕೆ, ಸೊ ವೆನ್ ದ ಸಾಲ್ವೇಷನ್ ಎಂಥಾಲ್ಪಿ ಈಸ್ more than the lattice enthalpy for the given solute and a solvent, then automatically the salt will dissolve. So based on this particular comparison, we can classify the salts as soluble salts, sparingly soluble salts, partially soluble salts are nothing but sparingly soluble salts, and some are totally insoluble in a given solvent. Okay, so you must know why water is a universal solvent, why most of the solutes can be dissolved there. Again, the nature of water, that is the polar nature, decides where the lattice enthalpy is less than the solvation enthalpy, so it will easily dissolve. So that is about solubility equilibria of a sparingly soluble salt. Here you have to understand about a constant, okay, that is usually we call it as a solubility product, okay, or solubility product constant. Okay, so try to understand first the basic thing about the nature of the solvent and the lattice enthalpy of the solute deciding the dissolution or forming a solution. Okay, now let me continue with the solubility product constant. Okay, now you have to understand solubility product constant we can express generally for sparingly soluble salts. Okay, let me take up one example, then you try to understand what is solubility product and how can we derive it for the different type of salts. Let me take up example of barium sulfate, BaSO4. is one of the examples for a sparingly soluble salt. It partially dissociates to give barium ion Ba2 plus and SO4 2 minus. Okay, so here if it forms a barium sulfate as a barium and sulfate ions, we can write a equilibrium constant as K is equal to, you know the expression, it is a concentration of Ba plus 2 into concentration of SO4 2 minus divided by concentration of BaSO4. Here you can modify it as K into concentration of barium sulfate is equal to concentration of Ba plus 2 into concentration of SO4 2 minus. Okay, now here the number of moles of barium and sulfate ions are 1 mole each. Okay, so the molar concentration we can express it as 1 mole per liter for barium and sulfate ions. Now if you consider the solubility in terms of S, okay, so this is a solid, you have to understand what we take it as a solid, and in the medium it is present in the aqueous form, these ions. So the concentration of solid we will not consider. With that reason we can represent it as solubility product constant, we write as KSP is equal to just concentration of Ba plus 2 and concentration of SO4 2 minus. As I told you just now, if we consider the concentrations in molar concentration, then we can take it as S mole per liter. This is also S mole per liter. So KSP is equal to S square. When you know the concentrations of the ions, or if you know the solubility of those two ions, you can easily substitute and get a solubility product constant. Are you clear? So this is easy way. When you know a salt which is a sparingly soluble salt, you have to remember only when the sparingly soluble salt is there, we can expect there is a reversibility, there is an equilibrium. So we can write an expression based on the solubility in terms of moles. Okay, if you understood this, let me take up one more example. So it looks very easy. I'll take up one more example and then we'll go for a generalization. Okay. I'll take up a second example now to understand the solubility product constant. Let me take up example aluminium sulfate Al2SO4 thrice. Now if it is a sparingly soluble salt, it dissociates partially. You know it forms aluminium Al3 plus and SO4 2 minus. Okay, you have to balance the equation. It is a Al2, so it is 2 moles of Al3 plus and 3 moles of sulfate. There is a difference. Okay, now we can consider the molar concentrations or we can consider the solubility in terms of moles. So Al3 plus I will consider as, if it is a 2 moles I will take it as 2s, and similarly sulfate solubility I can consider it as 3s. ಅರ್ಥ ಆಯ್ತಾ ಮಕ್ಕಳ? ಇಲ್ಲಿ 2s ಮತ್ತು 3s ಯಾಕೆ ತಗೊಂಡೆ ಅಂತ ಹೇಳಿದ್ರೆ ನಂಬರ್ ಆಫ್ ಮೋಲ್ಸ್ ಆರ್ ಡಿಫರೆಂಟ್. ಆ ಬೇರಿಯಂ ಸಲ್ಫೇಟ್ ಎಕ್ಸಾಂಪಲ್ಸ್ ಅಲ್ಲಿ ಏನಾಗಿತ್ತು, ನಂಬರ್ ಆಫ್ ಕ್ಯಾಟಯಾನ್ಸ್ ಅಂಡ್ ನಂಬರ್ ಆಫ್ ಆನಿಯಾನ್ಸ್ ಆರ್ ಸೇಮ್, 1 mole each. ಬಟ್ ಹಿಯರ್ ದ ನಂಬರ್ ಆಫ್ ಮೋಲ್ಸ್ ಆಫ್ ಕ್ಯಾಟಯಾನ್ಸ್ ಅಂಡ್ ಆನಿಯಾನ್ಸ್ ಆರ್ ಡಿಫರೆಂಟ್. ಇಲ್ಲಿ 2 moles ಇದ್ದಾಗ 2s ತಗೊಂಡಿದ್ದಾನೆ, 3 moles ಇದ್ದಾಗ 3s ಅಂತ ತಗೊಂಡಿದ್ದಾನೆ. ಸೊ ವಿ ಕ್ಯಾನ್ ಯೂಸ್ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಲೈಕ್ KSP is equal to concentration of Al3 plus and concentration of SO4 2 minus. Remember this, where the number of moles are raised to their respective powers. Okay, it is 2 moles means I'll write here 2. This is 3 moles means I'll write here 3. That you understood already in the equilibrium constant earlier. Okay, so we can substitute now. Al3 plus it is 2s to the power 2. Okay, it is 2s to the power 2 and this is 3s to the power 3. So on simplification it becomes 4s square into 3 cube is 27 s to the power 3. Okay, on further simplification it will become 108 s to the power 5. Okay, now this is expression for a solubility product for this particular salt. Okay, where S stands for the solubility in terms of mole per liter we express. Okay, so these are the examples where we understood how to get the solubility product constant. After these two examples, now let me move on to the general form. Okay, whenever there is a general form, how can you represent that solubility product constant? That part you try to understand. Okay students, we try to understand the general formula now. Suppose if I write AX, BY, A and B stands for the two different ions, X and Y for the different number of moles. So, if on dissociation what will happen? It is a solid which will produce ions in the aqueous form. So, what you can write is, I will tell you a very easy way of writing. You can write it as A plus and B minus. The first thing, one cation and one anion. So, how many moles of A? It is X moles of A, so we will write here X. How many moles of B? It is Y moles of B, so we will write Y here. Okay, why it is X moles? Because the charge here it is minus X. Why it is Y here? Because charge here it is Y. Okay, so now based on this, what you can write is, we can write a solubility product constant as Ksp is equal to, it is the concentration of A plus Y into concentration of B minus X, where that number of moles are raised to their respective powers. If it is X moles, it is power raised to X. If it is Y mole, power raised to Y. So you can represent the solubility product constant in terms of AB also. AX, BY, what we can write a general formula. Okay, so the charges are basically deciding the number of other ions to be formed there. So A plus Y power X and B minus X power Y. So this is about solubility product constant. Are you clear? So this is simple. Simple calculations may come. You no need to by heart the solubility product constant for all the salts. Okay, but depending on the type of salt, is it AB, is it A2B, AB2, you can go for simplification like this and you can easily get the expression for solubility product. Are you clear? So this is easy about solubility product constant. Students, we are in the last part of the equilibrium now. There is a common ion effect on solubility of ionic salts. Okay, so when you are understanding about a salt analysis, you study in the practicals also, the quantitative analysis and qualitative analysis is there. So you have to understand, in the qualitative analysis, in the detection of some of the radicals in the salt analysis, we use the concept of common ion effect and solubility. Okay, so it is the detection of some of the radicals by precipitation. Now to understand here, when the precipitation happens or how the common ion effect is responsible for the precipitation. Okay, now go back to the first part of this chapter when you studied about a Le-Chatelier's principle. Okay, you know, in Le-Chatelier's principle, if any one of the ions concentration is increased, then what happens? That concentration of ion, if it is trying to remain constant, it will combine with the other ion, means the oppositively charged ion, it will convert back into the salt or it may be precipitated. Okay, so you take any simple example or a general example, if one of the ions concentration is increased, it will combine with the oppositively charged ion so that it will convert into a precipitate. Okay, it will convert back to the salt. And in the same way, if one of the ions concentration is decreased, okay, if one of the ions concentration is decreased, then system tries to nullify that effect, so there will be more dissociation. Okay, so what you have to understand here, the solubility product constant Ksp and the concentration of the ions formed, that must become equal so that there is a formation of a precipitate. Okay, so here the one of the simplest concept you have to understand, I told you already, the common ion effect and solubility is used in the qualitative analysis. Let me give you one more easy example. Okay, suppose if I take a saturated solution of NaCl, saturated solution of sodium chloride if I take, and if I pass a HCl gas, if I pass hydrogen chloride gas into a saturated solution of NaCl, then what happens is the crystals of NaCl will be formed. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? ಇಲ್ಲಿ ಸೊಲ್ಯೂಷನ್ ಅಲ್ಲಿ NaCl ಡಿಸಾಲ್ವ್ಡ್ ಫಾರ್ಮ್ ಅಲ್ಲಿ ಇದೆ, ನೀವು ಅದಕ್ಕೆ HCl ಗ್ಯಾಸ್ ಪಾಸ್ ಮಾಡಿದ್ರೆ ಏನಾಗ್ತದೆ ಅಂದ್ರೆ ಸೋಡಿಯಂ ಕ್ಲೋರೈಡ್ ಕ್ರಿಸ್ಟಲ್ಸ್ ಫಾರ್ಮೇಷನ್ ಆಗ್ತದೆ. Okay, and the crystals of NaCl what is formed, it is pure form. Okay, it is a purest form and it can be used for many other salts in the purification also. And in HCl and NaCl, what is a common thing? That is a Cl minus. Okay, so due to the presence of common ion and even working on the principle of Le-Chatelier's principle, there is a formation of a crystals or there is a formation of a precipitate. Okay, so that is a easy application of common ion effect in the qualitative analysis. So simple, you remember the example, saturated solution of NaCl and we pass HCl gas into that, there is a formation of a NaCl crystals due to the precipitation, which is the effect of common ion present there. Okay, so there are so many other forms related to the common ion effect. You will understand in the salt analysis in detail. Okay, in the qualitative analysis we will go in detail with that, but here if we have this much knowledge about the common ion effect and solubility equilibrium, okay, it is sufficient. Okay, so with this we completed equilibrium chapter. Okay, so I think you understood. Just to come back with the what I told you in the ionic equilibrium, I started with the concept of ionic product of water, then we discussed about acids and bases, the weak acid and weak base dissociation constants. Okay, then we understood about some calculations there, okay, related to the pH. Then we understood common ion effect, buffer solution and solubility product constant. Okay, so remember the chapter is little lengthy but not difficult. It is very easy and interesting. Okay, so with this we will end the equilibrium chapter. Thank you.